Every year, the world produces over 60 million metric tons of aluminum, and a significant portion of this metal is turned into key parts for automotive engines. Did you know that over 75% of modern engines have aluminum cylinder heads? This choice isn't accidental. Lightness, strength, and the ability to withstand high temperatures make aluminum an ideal material. But what happens behind the scenes in the production of these critical components? How are tons of metal transformed into complex, high-precision parts? Today, we're diving into the fascinating world of industrial manufacturing, and we'll show you the whole journey, from raw material to finished cylinder head. Cylinder heads are most often made from two primary types of materials: aluminum alloys and cast iron. As of 2025, over 75% of modern automotive engines are equipped with aluminum heads, due to their lightness, good thermal conductivity, and the reduction of the overall weight of the power unit. One aluminum cylinder head assembly weighs on average between 10 and 20 pounds, whereas cast iron equivalents can exceed 40 pounds. Aluminum for such parts isn't just metal, it's a high-quality alloy, for instance with added magnesium or copper, which provides strength at high temperatures. The main suppliers of aluminum are countries like the People's Republic of China, which provides over 60 million metric tons annually, and India. In the United States, the majority of aluminum raw material is supplied by sea transport in the form of ingots or granules, which are subsequently remelted at local foundries. One standard 20-foot container holds up to 48,000 pounds of aluminum ingots, which is enough to produce over 1,000 heads. Cast iron, although less popular in new engines, is still actively used in heavy machinery and trucks due to its durability. Its production requires components: iron ore, coke, and limestone. The United States partially extracts ore itself, but imports a significant portion from Canada and Brazil. Rail transport is used. One typical train with raw materials can deliver 10 to 15,000 tons of iron ore to metallurgical plants. After the materials arrive at the facility, they undergo cleaning, sorting, and melting. For example, casting one cylinder head requires up to 22 pounds of aluminum, and the cycle from melting to cooling takes about 90 minutes. This is just the beginning of the production chain, in which each part goes through dozens of stages before being assembled onto an engine. Aluminum ingots or granules arrive at the plant in sealed containers. They are unloaded onto special platforms with automated cranes and delivered to the melting shop. Before melting, the aluminum is cleaned of impurities and moisture to avoid porosity in the finished casting. For this, the raw material is placed on vibrating tables with metal detectors or sorting conveyors. Robots or operators manually or mechanically reject unsuitable material. This is how contaminants, paint, oil, plastic, and shavings of other metals are identified. Thanks to quality cleaning of aluminum before melting, the rejection rate is reduced by 60 to 80%. The storage temperature for the raw material is controlled, about 70 degrees Fahrenheit, to avoid condensation, which can cause microbubble explosions if it gets into the molten metal. After cleaning from moisture and impurities, the aluminum is fed into large melting furnaces. These can be gas or induction units that heat the metal to approximately 1,220 degrees Fahrenheit. A stable melting temperature is maintained in these furnaces thanks to automated control systems, which prevents overheating and preserves the homogeneity of the future alloy. Furnaces typically have a volume of 5 to 10 tons, and one such furnace can produce up to 300 or even 500 cast cylinder heads per shift. One shift lasts 8 or 12 hours. The production flow is set up so that the molten metal is continuously supplied for casting, so even 15 or 20 minutes of downtime can cost the enterprise thousands of dollars due to lost pace and cooling of the material. Alloying elements are added to the molten aluminum, primarily silicon and magnesium. These elements increase the strength, heat resistance, and wear resistance of the finished part, making it suitable for operation under high pressure and fluctuating temperatures in the engine. As you can see, magnesium doesn't just improve human strength and wear resistance, but aluminum's too. After adding impurities, the alloy necessarily passes through a ceramic filtration system. Special porous filters capture oxides, microscopic particles of slag, and residual impurities. Without this filter, slag could get into the mold, form microcavities in the part's structure, and reduce its lifespan by tenfold. Filtration usually occurs in the ladle or holding furnace, where the molten metal is transferred from the main furnace. This is an intermediate stage where the metal is again stabilized by temperature and checked for chemical composition using spectrometers to precisely match tolerances. After cleaning and filtration, the molten aluminum goes to the casting shop, where it is poured into molds, a key moment when hot metal turns into a specific part, the cylinder head. This process must be extremely precise because the mold is complex, with numerous channels and cavities, and the engine's performance depends on the casting quality. Most often, gravity die casting or high-pressure die casting are used for head production. In the first case, the molten metal flows by gravity into a metal mold that can withstand several thousand cycles. In the second, the molten metal is injected under pressure up to 10,000 psi, ensuring precise filling of even the smallest channels. The mold, made of high alloy steel, is preheated to 400 degrees Fahrenheit or more to avoid thermal shock. The metal is supplied from a ladle or through an automated continuous feeding channel. A venting and gating system ensures air displacement, otherwise voids will form. The metal cools in the mold for 30 seconds to 1.5 minutes, after which the mold opens and the casting is sent on for further processing. Modern lines are equipped with sensors for temperature, pressure, and filling. The control system monitors the volume of molten metal, feeding speed, mold temperature, and metal temperature in real time. A deviation of more than 2%, and the machine automatically rejects the blank or adjusts the parameters. One casting station produces 40 or 60 heads per hour, depending on the technology. After the casting and cooling of the metal are completed, the next stage begins, removing the head from the mold. If sand casting was used, the mold is broken. It's a single-use structure made of a sand clay mixture, so it's simply broken apart to get the casting. In the case of die casting, a metal mold is used, which automatically opens, and the part is ejected by special pushers. At this stage, the so-called gray or rough blank is obtained, an unprocessed head with gates, risers, and irregularities. Its weight is 10 to 20 pounds, depending on the engine type and design. Almost immediately after removal, the heads are often sent for heat treatment. This typically includes quenching and tempering. The process involves heating to 1,000 degrees Fahrenheit, holding at that temperature, and controlled cooling. This strengthens the metal structure, increases hardness, wear resistance, and thermal stability, critical parameters for operation in the engine's hot zone. After heat treatment, the cylinder head proceeds to the computer numerical control machining stage. The head is secured on a fixture in a multi-axis machining center. A computer program precisely sets the coordinates, speed, and order of processing. Machining includes milling the mating surface to the engine block, drilling holes for bolts and other parts, boring channels for coolant and oil, forming valve seats and guides. One machining center can complete a full cycle in 10 or 25 minutes. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is? Or where it even came from in the first place? I mean, Everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us, and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning it up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. One barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet. And that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress, so there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Every single day, more than 15 billion cigarettes are produced worldwide. That is 173,000 every single second. But how does an ordinary tobacco leaf transform into a cigarette? What happens behind the closed doors of factories, where massive machines work non-stop to roll out thousands of packs every single hour? Today, we will reveal all the secrets, from enormous tobacco plantations to high-tech packaging lines. And you will be shocked at the hidden processes behind this industry. Stick around until the end so you do not miss the most fascinating details. The very first tobacco factory in Europe was established in Seville, Spain, in the year 1728. For over a century, this factory supplied Europe with cigars, generating substantial profits for the Spanish treasury. Today, Europe is home to major tobacco companies such as British American Tobacco, Philip Morris International, and Imperial Brands. For instance, in the year 2024, Imperial Brands reported an operating profit of £3.5 billion British pounds, which was 4.5% higher than the previous year. This growth was driven by a 26% increase in revenue from alternative products, such as electronic cigarettes and nicotine pouches. Growing tobacco requires a specific climate, as this plant thrives in warm weather and fertile soil. The primary regions for tobacco cultivation include North and South America, Africa, Southeast Asia, and Europe. The leading countries in tobacco production are Brazil, China, India, the United States of America, Zimbabwe, Turkey, and Italy. China is the world's top tobacco producer, cultivating more than 2 million metric tons of tobacco leaves annually, which accounts for over 40% of global production. The key tobacco growing regions in China are Yunnan, Guizhou, Hunan, and Sichuan provinces. India produces approximately 800,000 metric tons of tobacco per year, primarily in the states of Andhra Pradesh, Telangana, and Karnataka. Tobacco seeds are sown in the spring, and the leaves are harvested several months later. This process can take several weeks since each layer of leaves is collected separately. After harvesting, the leaves are transported to specialized facilities, where they undergo fermentation and drying. The most common drying methods include air curing, fire curing, or sun curing, depending on the type of tobacco. For instance, Virginia tobacco is fire cured, meaning the leaves are hung in curing barns where the temperature is carefully maintained using heated air. This process lasts about 7 to 10 days and gives the leaves a golden color and a mildly sweet aroma. Burley tobacco, on the other hand, is air-cured in shaded barns for an entire month, resulting in a more intense and dry flavor. After drying, the tobacco leaves go through fermentation, which helps reduce nicotine levels and remove excessive bitterness. This fermentation process can last several months. A large portion of the tobacco used for cigarette production in Europe is imported from Brazil, Zimbabwe, China, and the United States of America. Some countries, such as Italy, Greece, and Turkey, cultivate their own tobacco, which is also processed in local factories. Every batch of tobacco arriving at production facilities undergoes strict quality control, where factors like moisture content, color, and nicotine levels are analyzed. The process begins with the initial treatment of tobacco leaves. First, the leaves are sorted by quality and type, with damaged or unsuitable parts removed. On average, each cigarette contains approximately 1 gram of tobacco, meaning that large factories process hundreds of metric tons of raw materials daily. After sorting, the tobacco is processed in manufacturing plants, where machines take over most of the work. The leaves are first shredded into fine fibers. Machines meticulously control the size of these shredded pieces to ensure uniformity. Then, the tobacco undergoes steam treatment to increase its elasticity and improve storage conditions. Various flavorings and stabilizing agents are added to regulate moisture levels and enhance taste characteristics. Typically, cigarette blends include a mix of different tobacco varieties to achieve the desired flavor and strength. The next stage is cigarette formation. Production lines are equipped with specialized machines capable of rolling out more than 20,000 cigarettes per minute. These automated lines operate with incredible speed and precision. The process begins with shredded tobacco being evenly distributed onto a conveyor belt. Next to this belt, a continuous strip of cigarette paper is unrolled. The machine wraps the tobacco in the paper, forming an uninterrupted tube that resembles a long roll. This roll moves along the belt at high speed, and special cutting blades then slice it into individual cigarettes, each approximately 3 inches long. Filter production is a separate process that begins with a primary material, usually acetate fiber. This synthetic polymer is derived from cellulose, which comes from wood pulp. The fibers are treated with special chemicals to give them the required structure, after which they are pressed and formed into long strips. To bind the fibers, a plasticizer called triacetin is used, ensuring the filter maintains its shape. These long strips are rolled into cylindrical blanks, which can be several feet long. They are then cut into smaller sections that match the required filter length. On the production line, these filters are fed into a specialized mechanism that wraps them in a thin paper layer to reinforce their structure. A standard filter can weigh between 10 and 20 grams, depending on the type, and its volume can range from 1 to 3 milliliters. In large-scale manufacturing, several metric tons of acetate fiber may be processed daily, with the total volume of filters produced reaching hundreds of thousands of liters. Next, the filters are attached to the tobacco rod. This is done using wrapping paper that is bonded with food-grade adhesive to create a strong connection between the filter and the tobacco-filled portion. In the bonding area, the wrapping paper passes through a roller that evenly applies the adhesive to its surface. The filter and the tobacco rod are then precisely aligned and merged using a specialized mechanism. The wrapping paper is tightly wound around the connection point and firmly pressed to ensure a secure bond. This process happens in a fraction of a second, and each minute, the machine can attach hundreds of filters to tobacco rods. Throughout production, the total amount of adhesive used can reach several dozen kilograms per shift, while the length of tobacco rods passing through the equipment is measured in hundreds of yards. Once assembled, the cigarettes move along the conveyor to the inspection section, where the strength of the bonds, uniformity of the wrapping, and adherence to standard dimensions are checked. Special scanners and weight sensors examine each cigarette to detect any defects, such as hollow spots, uneven tobacco distribution, or damaged paper. Any defective items are automatically removed from the line. Another crucial step is the application of tracking codes on each cigarette or filter, ensuring full traceability throughout the production cycle. This is done with high-precision laser markers that do not damage the paper. Finished products are then cut to final lengths if needed before reaching the packaging section, where they are grouped into packs of 20 and wrapped in foil. Once cigarettes are paired with filters and pass quality control, they move to the packaging stage. First, the cigarettes are aligned on the conveyor, forming groups based on the intended pack size. A standard pack typically contains 20 cigarettes, although there are variations with 10 or 25 pieces. Once grouped, the cigarettes are wrapped in an inner lining made of foil paper or thin aluminum foil to maintain freshness and prevent drying. They are then automatically placed into cardboard boxes, which arrive via a separate conveyor. These boxes are made from thick cardboard that is pre-cut, folded, and glued using high-speed machinery. The packs then pass through a wrapping mechanism, which seals them in a thin, transparent film. This film includes a perforated strip for easy opening. At this stage, excise stamps and barcodes are printed. On average, a single packaging line can process about 15,000 packs per hour. Completed packs are arranged into blocks of multiple packs, usually 10 per block. These blocks are further wrapped in film or packed into cardboard boxes before being placed onto pallets for transportation. Large cartons can hold up to 500 packs each. The boxed products are stored in factory warehouses until they are shipped to distributor warehouses. From there, cigarettes are sent to stores, supermarkets, and specialized kiosks. Every day, dozens of trucks leave major tobacco factories, delivering millions of cigarettes to distributors and retail locations. The entire journey, from manufacturing to store shelves, can take anywhere from a few days to several weeks, depending on logistics and market demand. At large tobacco factories, machines operate continuously across multiple shifts. In a single workday, one of these machines can produce several million cigarettes. Modern cigarette manufacturing is characterized by a high level of automation, minimal human involvement in production, and rigorous quality control at every stage. Factories are equipped with air quality management systems to maintain stable humidity and temperature, which are crucial for preserving tobacco properties. A typical tobacco factory can produce up to 200 million cigarettes per day, amounting to thousands of metric tons of finished products each month. Every year, more than 22,000 short tons of amethyst are mined all over the world. But how do these unique purple crystals end up on display in jewelry stores? Picture enormous geodes, each roughly the size of a person, packed with dazzling crystals that miners extract from remote regions in Brazil, Uruguay, and Africa. Some of these geodes are so rare that they are transported by helicopters. However, did you know that only about 10% of all discovered amethysts are of jewelry quality? Let us dive into a world where nature creates masterpieces and humankind unveils them for everyone to see. Brazil is one of the largest suppliers of amethyst on the planet. The main deposits are located in the states of Rio Grande do Sul and Minas Gerais. In Brazil, amethyst geodes are often found, which are hollow stone formations lined with crystals on the inside. Some geodes can reach over 9 feet in height. Uruguay is famous for its amethyst that has a rich, dark purple hue. This stone is usually of higher quality than the Brazilian variety. Geodes from Uruguay are considered extremely valuable because of their depth of color. The African continent, particularly Zambia, is also an important source of amethyst. Zambian amethysts feature a unique purple color with a bluish tint. They are mined in considerable volume, but the deposits are located in hard-to-reach regions, making transportation more complicated. Amethyst deposits in the United States are not as large-scale as in Brazil or Uruguay, but they have their own special history and appeal. The amethyst found in the United States is prized for its vibrant coloring, historical significance, and local popularity. So, let us take a closer look at the main locations and their distinctive features. Four Peaks is the most renowned and likely the largest amethyst deposit in the United States, situated in Arizona, at an elevation of about 7,545 feet above sea level. The amethyst from Four Peaks is noted for its deep purple color with a subtle reddish glow. Many believe these stones can compete in quality with even the most valuable specimens from Uruguay. The deposit is located in an extremely challenging spot. There are no roads, so miners and equipment are transported by helicopters or on mules. This is one reason why stones from this deposit are so expensive. The mining process is physically demanding and costly. Most of these mines are small, and much of the work is done manually to avoid damaging the crystals. A modest region in the northern part of Georgia is home to lighter, pastel-toned amethysts. Although the deposits are not as extensive as those in Arizona, the stones exhibit a unique clarity and a pleasant purple hue suitable for more affordable jewelry. Local specimens are often mined in small private shafts or even during special tours that allow tourists to try their hand at being treasure hunters. This aspect adds a certain charm to Georgia amethysts, as they become both a souvenir and a cherished memory. The Creede area in Colorado was once more famous for its silver mines. However, there are certain spots where amethyst deposits can be found as well. These stones tend to be lighter in color and less intense in saturation, yet they possess interesting inclusions that give them a unique character. Amethysts from Creede are frequently used to make cabochons, which are smooth, unfacetted stones suited for decorative ornaments. Amethyst usually forms in volcanic rocks, where high temperature and pressure conditions cause quartz to absorb iron impurities, then cool over thousands of years. The outcome is a deep purple crystal that makes you pause and exclaim, "Wow!" For example, in Brazil, miners uncover enormous geodes lined with crystals. Sometimes these geodes are so large that they appear at exhibitions, where people take photos beside them, as if they were standing next to a work of art. Now imagine this scene: a team of miners wearing hard hats, equipped with headlamps and pickaxes, searching for just the right pockets of stone where these priceless cocoons lie hidden. Believe me, it is no simple task. Today, miners do not rely solely on luck in their pursuit of amethyst. Their primary allies these days are science and technology. The process starts with detailed geological mapping. Geologists investigate regions that are well known for containing abundant quartz, the primary mineral from which amethyst arises. For instance, in Brazil, the world's largest amethyst producer, researchers target geological formations ranging in age from 50 million years to 200 million years. One of the most advanced tools is high-resolution satellite imagery. Through spectral analysis of the colors on the Earth's surface, specialists can pinpoint hues that hint at the presence of specific minerals, including quartz. Moreover, seismic sensors contribute to the creation of three-dimensional models of the underground layers of soil. These devices detect even minute reflected waves that tell the story of the materials hidden below the surface. Yet, as strange as it may sound, intuition and hands-on experience still play a huge role. For instance, miners in Rio Grande do Sul in Brazil claim that deep reddish-brown soil nearly always indicates proximity to amethyst. Such observations help them concentrate their efforts exactly where the odds of discovering stones are the greatest. Statistics show that only about 5 to 10% of all areas that look promising based on maps or satellite data actually harbor commercially valuable deposits. In Brazil, which accounts for over 40% of the global amethyst market, dozens of new zones are surveyed every year, but only a handful proceed to the extraction phase. The average depth of an amethyst mining site seldom exceeds a few dozen feet, but these locations demand enormous amounts of preliminary work. According to the United States Bureau of Mines, launching a single mine may require as long as 3 years and cost anywhere from $50,000 to $100,000 before unearthing even a small pocket of amethyst. This illustrates how labor-intensive and expensive the quest can be, even for gems as popular as amethyst. Ultimately, technology, expertise, and a hint of intuition collaborate to uncover those mysterious purple treasures that we admire in jewelry. Although the probability of finding the ideal crystal is slim, and the miner's work is strenuous, the reward is unquestionably worthwhile. The amethyst extracted from a mine looks nothing like what you see in a display case. It is often covered in rocky residue, irregular in shape, sometimes almost opaque. Once it is mined, the stone goes to a factory, where a kind of magical transformation unfolds. First, the crystals are cleaned, occasionally by hand, and occasionally in massive tumblers that literally scrub away the dirt. Then each stone is sorted by quality. Here is the interesting part. Only about 10% of all the amethysts unearthed are of jewelry-grade quality. The rest are used for more budget-friendly accessories or even ornamental items. The next step is cutting. This is a true art that merges careful science with the delicate touch of a skilled artisan. Picture a person peering through a loop, meticulously turning the stone to find the ideal angle. The most fascinating aspect? One slip of the hand can cause the crystal to crack. Let us suppose the stone is finished. The next issue is transportation. This task is not as straightforward as one might initially assume. Certain amethysts travel in specialized boxes, padded with foam inserts to protect them from the faintest jostles. In the case of geodes, they are often packed in wooden crates lined with soft materials. Uruguay has a distinctive export program for its amethysts. Stones are sold directly at auctions, drawing buyers from all over the globe. In Brazil, on the other hand, most of the output goes straight to large enterprises that handle both cutting and further distribution. The price of amethyst is determined by factors like color, clarity, and size. The most expensive pieces boast a vivid purple tone with a slight reddish shimmer, often called deep royal. Such stones are frequently utilized in luxurious jewelry, which can appear at international auctions. Here is something surprising. Even though technology has improved remarkably, a great deal in this field still hinges on human effort and observation. It is a tradition passed down through many generations. Even the extraction itself relies more on manual labor than on large machinery. Initially, after identifying a promising zone, preliminary work begins. If the amethyst is near the surface, excavators remove the topsoil, creating large open pits. In places like Minas Gerais and Bahia in Brazil, these open pits can span several dozen feet across. However, if the amethyst is buried deep, the operation goes underground. Mines that yield this crystal can extend about 320 feet into the earth, forming a vast maze of tunnels branching out in all directions. Breaking through the tough layers of rock is the first step to reaching amethyst. This may involve using explosives or drill rigs, but it is not as dramatic as one might imagine. It must be done very carefully to avoid shattering the precious crystals. The people responsible for this work are genuine experts. They even live by an informal motto: "It is better to go around than to destroy." A carelessly managed blast can reduce a stone to fragments. Once the deposit is exposed, miners proceed by hand or with small tools to gently dislodge the crystals. Envision the scene: darkness, illuminated only by the glow of headlamps, and silence broken by the occasional strike of a pickaxe or the hum of a handheld saw. Everything relies on the miner's dexterity. Even the most subtle motion can determine whether a crystal remains intact or breaks. Some refer to this phase as jewelry-level work. The amethysts that are found are typically surrounded by quartz rock and clay, so they are cleaned right there in the mine. This is painstaking work, removing layer after layer and taking care not to harm the delicate crystal structure. It is reminiscent of restoring an antique vase. The most valuable crystals are separated by hand, with every movement carefully planned. Interestingly, the ambience in these mines can be quite a spectacle. For example, in the famous Las Vegas mine in Uruguay, amethysts shimmer in the darkness under the beam of a lamp, creating the sense of stepping into a magical subterranean realm, radiating shades of purple and blue. In some locations, such as the Amethyst Park in Brazil, the mines are open to visitors, and people can witness firsthand how skilled workers gently extract the crystals from the walls. Those workers are the real heroes. They toil in challenging conditions. Imagine a place where the trains of the future are born every single day, a place that brings together innovation, sustainability, and history. The Siemens Mobility Factory in Sacramento is over 2 million square feet of manufacturing space, creating the locomotives that move America. Here, one of the largest 3D printers in the world is installed, and up to 80% of the energy comes from solar panels. Curious about how trains are tested? They are run on specialized tracks to evaluate speed, noise, and stability. This is not just a factory, it is a true innovation lab. The story of this factory began back in 1984, when Siemens decided to invest in the future of rail transport in the United States. But they needed more than just technology. They needed a reliable base, and Sacramento was the perfect choice. What does the capital of California have to do with train manufacturing? Actually, the location choice was very strategic. Sacramento has a long history of railroad infrastructure. As far back as the 19th century, this city was one of the key hubs of the Transcontinental Railroad. In other words, the railway spirit has been alive here for over 150 years. Additionally, the region had access to a large number of skilled workers who could contribute to manufacturing. On top of that, the proximity to ports and other transportation hubs in California ensured smooth logistics. When the factory first opened, it was relatively small. Siemens Mobility was just beginning to build its brand in the United States. Initially, the factory specialized in manufacturing locomotives and trams. However, the company's ambitions were massive. They saw the need for modernizing American rail transport and decided to become part of this revolution. Within just a few years, the factory began scaling up production while implementing cutting-edge technologies. Over time, it started producing trains that you can now see in dozens of American cities. The Siemens Mobility factory continued to grow. In the 2000s, it began producing modern high-speed trains and electric trains that meet the highest standards of comfort and energy efficiency. One of the key milestones was the expansion of the manufacturing facilities. The factory grew to over 200,000 square meters. This allowed for increased production capacity, the addition of new car manufacturing lines, and even testing grounds. Today, the Siemens factory in Sacramento is one of the most sustainable manufacturing sites in the world. Approximately 80% of its energy comes from on-site solar panels. Water usage is maximized for efficiency, and nearly all material waste is recycled. By the way, this factory produces trains for Amtrak, Brightline, and various urban rail systems, including the Los Angeles Metro and Minneapolis streetcars. The factory emphasizes localization. About 90% of the materials used in train manufacturing are supplied by American companies. This not only reduces logistics costs, but also supports the local economy, enables quicker responses to market needs, and ensures that the products meet client requirements. Siemens Mobility does not stop innovating. They are already working on trains with hydrogen engines and autonomous driving systems. While specific statistics on these projects may be limited due to commercial confidentiality, it is known that the company invests significant resources in research and development in these areas. So, how are trains made? It all starts with large sheets of aluminum and steel, which are cut and formed into components for train cars. And you know what? I was amazed by how organized the process is. Even at the stage where you are just looking at pieces of metal, everything is planned down to the smallest detail. Assembling a single car can take weeks, and an entire train, months. But the result is worth it. When they arrive at the factory, they are immediately distributed into zones based on what will be made from them: walls, floors, roofs, or smaller components. This is not just a pile of metal. It is all sorted and labeled with special codes. This ensures that no piece gets lost and that production does not halt due to confusion. The metal is cut on specialized machines that use lasers or plasma cutting, and there is no room for error. Every piece is cut with millimeter precision. But here is the interesting part. There is almost no waste. Leftover pieces are reused to create smaller components or sent for recycling. This is not just cost-saving, it is sustainable. The metal is used, for instance, to create train car exteriors. These are made of aluminum for a good reason. This material is both lightweight and strong, making it ideal for high-speed trains. I was even told that it is environmentally friendly. Aluminum can be recycled almost infinitely. Impressive, right? Cutting robots and hydraulic presses create parts that undergo further processing. Everything here is ultra-precise. There is no eyeballing it. In the next workshop, the train's frame is welded. Once the car bodies are ready, robots and highly skilled workers step in. I watched as each part was installed one by one, from roofs to floors, from walls to doors. It is like a massive Lego set, but on a scale you can hardly imagine. In this workshop, the car frame is born. Every weld is checked to ensure it can withstand future loads. Imagine sparks, bright lights, and sounds like in a blacksmith shop, but with robots. Workers install windows, doors, seats, electrical systems, ventilation, everything that makes a train comfortable for passengers. Next, the train is painted with weather-resistant paint. And yes, everything here is as eco-friendly as possible. Filters capture harmful substances to prevent environmental damage. But the most fascinating part starts with the details. Did you know that every train car interior is essentially a small universe? Wiring, control systems, air conditioning, seats, everything is installed with meticulous precision. One worker even joked, "Every single screw here is worth its weight in gold." Another thing that amazed me was how many processes are automated. For example, electronics inside the cars are tested using special simulators. It is like a video game where the system checks if all buttons, displays, and even Wi-Fi are working. Now picture this. Before a train hits the tracks, it is tested on a special track. Yes, they literally run it here to measure speed, stability, and even noise levels. Watching this giant accelerate is a whole new level of satisfaction. Here is what makes factories like Siemens Mobility special. Everything works in harmony. On one hand, there are people working with their hands, putting a piece of themselves into every car. On the other hand, there are robots and automated systems making the process faster and more precise. I was even shown one of the largest 3D printers in the world, which prints train parts. Imagine this. Instead of waiting for parts to be delivered from across the globe, the factory can make them right here, right now. It is not only convenient, but also eco-friendly. Less transportation means fewer emissions. For instance, the 3D printer produces mounting nodes, frame elements, and even special ventilation components. Traditionally, these would need to be cast or welded, but here everything is done more precisely, faster, and more efficiently. Fairings, structural components, interior details, spare parts, and prototype versions of parts can all be printed, saving materials and time. Okay, some might ask, what is so special about this? Trains are just trains. But no, each of these modern cars is a step forward in transportation development. More sustainable materials, energy-efficient systems, passenger comfort, all of this impacts not just us, but the future of our planet. Moreover, factories like the one in Sacramento create jobs and introduce new technologies that can later be applied in other industries. It is a place where technology and people come together to create something truly remarkable. Oh, you cannot even imagine how massive this factory is. The Siemens Mobility facility in Sacramento spans approximately 2 million square feet. Picture several football fields connected into one giant structure. It is a city within itself. Workshops, conveyors, rail tracks, repair shops, and even test tracks for finished trains. The factory is divided into several zones, each responsible for a specific stage of production. When I left the factory, I felt like I had visited the future. This is a place where innovation, craftsmanship, and human talent combine. If you ever get a chance to visit something like this, do not miss it. It is truly impressive and changes how you see the world. So, are you ready to hop on a train next time and think, how was this made?